In this video, we introduce Sungkhan Chang's solution of problem A2, of 2014 Putnam competition. Let A be the n by n matrix, whose entry in the ith row and jth column is 1 over the minimum of I and j. Compute the determinant of the matrix A. Let us review a few things about determinants. If one of the rows or columns is a scalar multiple of the other, then the determinant is 0. If we swap two rows or two columns, the determinant changes its sign, but the magnitude of the number remains unchanged. When elementary row operations are applied, other than swapping rows, determinant remains unchanged. Here is one explanation. This operation seems a little unpopular in the first linear algebra courses, but it is in fact a very interesting one. It is one of the elementary row operations. Namely, adding a scalar multiple of one row to another. In this case, k times the row w1 is added to the second row. Let me point out that those are hyphens, not minus symbols. They are just indicating they are row vectors. Let us explain what happens to the determinant when we do this row operation. This manipulation is due to the multilinearity of the determinant map. The determinant map distributes over the addition in the second row in the left-hand side, while all other rows are kept exactly the same. In other words, linearity is applied, one row at a time. If we view a matrix as a collection of column vectors, this principle applies the same way. Now the observation is that, in the second term of the right-hand side, the second row is a scalar multiple of the first row. Therefore the second term is 0. So it shows that such an elementary row operation does not change the determinant. For upper triangular matrices, computing the determinant becomes easy. It is the product of the diagonal entries. So, for this 3 by 3 matrix, it is A times B times C. This suggests that by doing elementary row reduction, we arrive to an echelon form, whose magnitude of the determinant is equal to the determinant of the original matrix. This is an example where n is 3. Let us describe the pattern of entries for u. Along the diagonal, we have 1 over I, since I and j are equal to each other. From a diagonal entry, to the right and to below, the entries remain constant. As we go through those entries, the index of rows or columns increases, while the other index remains constant. So the minimum will not change, and this seems like a general explanation. Notice that the first two entries of the second and third row are equal to each other. We will subtract the second row from the third row. So we have 2 zeros and 1/3 minus 1/2. Notice that the first entries of the first and second rows are equal to each other. If we subtract the first row from the second row, we obtain the second row in this third matrix, which is in echelon form. Thus the determinant is the product of the diagonal entries. We shall take a look at the case of n equal to 4, and introduce manipulation that clearly suggests an induction structure. These are the bottom two rows of the matrix of 4 by 4. If you recall the pattern of entries, you can verify that these are correct entries. By subtracting the top row from the bottom, we have those 3 zeros. Now I am showing the whole matrix. You may notice that the 3 by 3, upper left corner sub-matrix is the earlier one we considered. So if we do the row operations for the case of n equal to 3, to the first 3 rows of this one, then we obtain an echelon form, while that alone does not tell us about some entries in the fourth column. However, to compute the determinant of an echelon form, we do not need that information. Rather than applying row reduction to a sub-matrix, we may consider using mathematical induction. One popular way of computing determinant is to use Laplace expansion. Since we have zeros at the bottom row, the first level of expansion becomes a single-term expression. Recall that there is the alternating sign rule for each term in the expansion. If n is even, the sign assigned for the lower left corner is negative. But as we go across to the lower right corner, it becomes positive. If n is odd, the sign assigned for the lower left corner is positive. And as we go across to the lower right corner, it stays positive. For both cases, the sign for the lower right corner is always positive. 1/4 and 1/3 came from the bottom right corner, and it is clear that if this is an n by n matrix, we have a factor of 1 over n, minus 1 over n minus 1. Although we have not stated an induction statement clearly, it seems easy enough to bring in the induction hypothesis for the matrix, appearing in the Laplace expansion. So please allow us to omit the induction setup, and claim the result. This is the claim. If we apply the induction, it will fall out easily with that Laplace expansion. Now if we combine the fractions of each factor, we pick up n-1 copies of negative ones. Altogether, the denominators can be regrouped into n factorial times n-1 factorial. This seems like a simple enough formula to state. Thanks for watching.